Hi everybody, welcome to our lecture on audio coding. So for the start, here's some organizational details and overview. So the lectures consist of 14 lectures read by me, Gerald Schuller, and those lectures will be available as video online in Moodle 2 and on YouTube. Then there will be seminars or practice lessons with Oleg Golokolenko. So you will get periodic homework assignments and also quizzes, which will count together 30% towards the final grade. Right. So you should build small groups, like 2 to 3 people, to solve the homework, although the quizzes needs to be done individually. But the homework assignments are programming assignments, and they are best done and checked by having groups of 2 to 3, although individually you can also do it if you want. Right. Yeah, there will also be tutorials which we have on our Moodle 2 website. And basically everything, the communications and also the slides will be available on Moodle 2. So make sure that you're registered there. Then we will have an exam. We will have a final exam and also a midterm exam in the middle of the semester. And the final one is 90 minutes. Then all the material and more is covered in our course book, which just came out this fall. It's called Filter Banks and Audio Coding, Compressing Audio Signals Using Python, where I'm the author. And here's the link. So let me open this link. So here you can see the link to the book. So this is our course book. And it contains all the content of our lecture and also the Python examples that I will show. And the Python examples are also available on our GitHub repository of our group on Applied Media Systems. So you can buy this, or you could also try to check it out from the library. They should also have it at some point. Not immediately, but I guess soon they should have some versions available for checking them out. Okay, so the book basically covers most of the material, or more than the material that we will cover here in the lecture. And the prerequisites that I assume that you have are the lectures Advanced Digital Signal Processing. This is for beginner master students. So here you can also see the website. So this is a website for it, and there you can also see you have all the slides available as PDF here. So and just in case you want to refresh your knowledge, you can take a look there. Another prerequisite is multi-rate signal processing. So here you can also see a link. So this is usually mid-level master students. And again, here you can see all the slides in case you want to refresh your knowledge. So both are lectures given by us. ADSP is in the winter semester, so right now, and multi-rate signal processing is in the summer semester. Yeah, and for access to papers regarding audio coding, there's also a free access available to the IEEE database via the university library from within the TU Ilmenau network using this link here. So using this link you get to the IEEE paper database. So that's quite huge. Yeah, we also assume that you are familiar with Python because we use Python for our seminars and I also use it as examples for the lecture. So this is really important that you're familiar with it, and if not, take a tutorial or also take a look at our bachelor course, Basics of Video Technology. So in Moodle we have a link to a tutorial, and here this link you can also use for checking out the introduction into Python. So you can see it. So here you have the lecture slides in English. So here you have some introduction, and here you have some more video introduction. So the first two lectures contain also a Python introduction here. Okay, so that leads me to a recap of the basics of multi-rate signal processing. So what's coming now is basically stuff that you should be familiar with. It's just a recap to refreshen your memory. Yeah, so audio coders process sampled audio signals. As an input signal, they often have audio signals sampled at, for instance, 48 kilohertz or 44.1 kilohertz. So this is for the CDs, for instance, the standard sampling rate. And usually it's 16 bits per sample. That's the most common used number of bits per sample. And this is also identical to what's used at CDs, audio CDs. Internally, they filter the signal and down or upsample it with filter banks. So the encoder is doing downsampling, the decoder is doing upsampling. Yeah, so in the encoder and decoder. Hence, before we take a closer look at the filter banks, we first take a short look at the basics of multi-rate signal processing. So here, sampling, downsampling, upsampling, and starting with sampling an analog signal, which leads to normalized frequencies. So to see what happens when we sample a signal, let's start with analog signal s of t. So lowercase t means here it's the continuous time variable. Sampling it means to sample the signal at time intervals of t, capital T. So this is, for instance, 1 over 48,000th of a second, so that we have 48,000 samples per second. So t would be a few milliseconds, or with a sampling frequency fs. So this fs, the sampling frequency, would be either 48,000 in my example, or 44,100 if it comes from the CD, the audio CD. So mathematically, sampling can be formulating as multiplying the analog signal with a Dirac impulse at the sampling time instances n, lowercase n, times uppercase t. So t was given by the sampling frequency, and lowercase n is an integer, 0, 1, 2, 3. Right? So that's the number of our sample. And if you assume causal systems, meaning they only depend, they start at some point, so then we have n, we can set the first sample to n equals 0. So if we look at the Fourier transform of an analog time continuous system, we get this. So here you can see actually t starts at minus infinity, so this is non-causal, and goes up to infinity. So this is the more general case. So the Fourier transform is fairly generic, right? So we just assume that s starts at some point in time, so that this t minus infinity is more like for theory or to cover any starting point. Yeah, and probably you should be familiar with this transform. So we have our signal, the analog signal in the analog time domain. We multiply it with this transform kernel e to the minus j omega t, and then we apply this integral over all times. And this omega here is our frequency variable, which then appears as the result of this integral, right? So t is gone because we integrate over all t's, so what's left now is instead having an omega So now we have the Fourier transform in the frequency domain, omega. And since this e to the j omega, according to Euler's equation, is cosine omega t plus j sine omega t, that means we have also an imaginary part, and that also means that this Fourier transform is complex valued. So even if S is real valued, coming from a microphone, for instance, having positive and negative float values, S of omega will be a complex result. So it has an imaginary and a real value, real plus j imaginary. And j is our imaginary unit. Yeah, the superscript c denotes the continuous version, so here for continuous. And this omega is our angular frequency 2 pi f. So here we just have a 2 pi because that's the periodicity of this exponential function. Remember, e to the jx is the same as e to the jx plus minus 2 pi or multiples of 2 pi. And that's why we have this 2 pi periodicity. So basically we can describe each period of our sampling interval as going once around the circle. Yeah, if we now compute the Fourier transform for the sample signal, we get a sum because the Dirac impulse is not zero, only at the sample time instances, right? So if this t only lives in multiples of capital T, then this integral turns into a sum, right? Because the integral over a Dirac impulse is 1. So here, if this only lives at the sampling intervals where we have a Dirac pulse, then this integral over each of those Diracs will be 1, and what's left is just the value of s at time instance nt, right? And this leads us to this result. So here we have s of nt times e to the j omega, and now instead of having lowercase t, we just have this n capital T, right? So this is now the result for sampled version, and that has some important consequences. So first, the superscript d is now denoting the discrete time version. Now we can see that the frequency variable only appears as omega times n times t. So appears together, let's say together. So we always have this omega and t, and this t is constant, right? And t is the inverse of the sampling frequency. And hence we get omega times capital T is omega divided by the sampling frequency. And this is now our normalized frequency, right? So here we normalize to our sampling frequency, Fs. And if for our sampling frequency, this will be just 2 pi, right? So imagine this omega is 2 pi fs, then we have 2 pi fs divided by fs is 2 pi, right? So if omega represents the sampling frequency, then pi is 2 pi is the result, and half of our sampling frequency, as we know, is the so-called Nyquist frequency, which is the upper limit of our usable frequency range, right? So assume we have a sampling rate of 48,000 samples per second, right? Then our omega for this sampling frequency would be 48,000 times 2 pi, and then we divide it by 48,000, and the result is 2 pi. Half of it is pi, and that corresponds in the before sampled version to half of 48,000, so that would be 24,000. And this 24,000 hertz is also the upper limit of our usable frequency range. So turns out 24,000 is a frequency which we cannot, which we can just not represent anymore. Anything below 24 we can represent with this sampling rate. So for instance, 20 kilohertz we can represent, but 24 we cannot represent anymore because of Nyquist. Nyquist says our frequencies need to be strictly lower than the Nyquist frequency. So strictly lower than 24 kilohertz in this example. Yeah, so important point here is we have a normalized frequency, normalized to the sampling frequency, where 2 pi denotes the sampling frequency and pi is the Nyquist frequency, since we have no time units in a sample sequence. So that's also very practical because we don't need to worry about the exact sampling rate anymore. We always know that pi is Nyquist and 2 pi is the sampling frequency, independent of the sampling hardware we are using. So that actually simplifies the math that we have, and simplifying is always good, right? And also it gets rid of units. If we have hertz, which is 1 divided by second, in our original time domain, then if after we divide by the sampling frequency, which also has the unit of 1 over second, then those units cancel, right? So after this normalization, it's unitless. So that's another convenient. We don't need to worry about units. All we need to worry about pi and 2 pi because these are Nyquist and the sampling frequency. Yeah, and to indicate that we are now in the discrete time domain, we rename our signal to x of n. So just having the lowercase index, the integer index in discrete, I should call this discrete time domain. Okay. Yeah, so this simplifies our notation. Yeah, now we can also apply the Fourier transform to it, but now it's the discrete time Fourier transform, right? Because we only have integer, we have samples, discrete samples in time, right, depending on this integer value n. And the discrete time Fourier basically looks like what we derived before, except that we now can replace lowercase omega divided by fs with this capital omega. Right, same here, we replace this lowercase omega by the normalized frequency capital of omega. And then the sum stays the same, basically. So this is the resulting discrete time Fourier transform. Yeah, and that has some interesting consequences, because lowercase n in the exponent here is integer. It's no longer real valued like lowercase t. And that means we get a 2 pi periodicity for x of omega. And that's because this e to the j omega is 2 pi periodic, because this is integer. So imagine n is equal 1, then it's easy to see that we have this 2 pi periodicity. If n equals 0, then this is just 1. So basically it has an infinite period. So for and for higher n, like 2, 3, 4, the period becomes shorter. So 2 pi divided by this n then. And what they all have in common is this 2 pi periodicity. And that's why this sum is also 2 pi periodic. And this is the first important property for discrete time signals. The above transform is called the discrete time Fourier transform, not the discrete Fourier transform, which is for finite or periodic time sequences. So here the DTF, the DFT is for finite or periodic sequences. So maybe I should make this closing bracket here. So here basically we still assume that we have an infinitely long signal. So here we still have an infinite block length. Also observe that for real valued signals, the spectrum of the negative frequencies is the conjugate complex version of the positive frequencies, right? So here the spectrum of the negative frequencies is obtained as the conjugate complex version of the positive frequencies. And you can see here that indeed negative frequencies are not exactly the same as positive frequencies here in this case because of this conjugate complex operation. So there's actually a reason for having negative frequencies, and this is because when we have complex sequences, then even the symmetry does not hold anymore, and then it really makes sense to have positive and negative frequencies. Yeah, so x over bar denotes the conjugate complex operation, and this is because in the sum of our DTFT we have this complex exponential, and when we replace omega by minus omega, basically we can multiply out the minus 1 here, then the two minuses cancel, then we have just j omega n, and this is the same as taking e to the minus j omega n conjugate complex. Right? Taking this complex exponential conjugate complex is just changing the sign of the exponent, and that's why this is true. And also for this to hold, we need to have this real valued signal, because when we have real values in this sum as signal x, then the conjugate complex does not change. So conjugate complex of a real valued signal is the same. Yeah, so this gives us the normalized frequency, and also this property that for real valued signals we have this symmetry between positive and negative frequencies. And this is also the reason why for real valued signals we just need to look at the positive frequencies, right? And particularly the positive frequencies between 0 and pi. Because of 2 pi periodicity, we know that the frequencies from pi to 2 pi are identical to 0 to minus pi, right? And again, it would repeat because of this symmetry. So basically this says also that for real valued signals, we just need to consider the frequency range from 0 to pi, which is basically the same as Nyquist says, because pi is the Nyquist frequency. Yeah, so next, if we have the signal already sampled, now we want to further sample it, for instance, in our audio coder. So what happens if we further downsample an already discrete signal x of n to reduce its sampling rate? Downsampling by capital N means we only keep every nth sample and discard every sample in between. This can also be seen as first multiplying the signal with a sequence of unit pulses, so here it's not Dirac but just unit, which means we have a 1 at each sample position that we want to keep, and zeros in between. So basically we zero out the samples that we don't want to keep. And later we drop the zeros. So it's just like with the Dirac impulses, but now with the ones instead of the Dirac impulses. This multiplication with this unit pulse train can now be used to mathematically analyze this downsampling, first still including these zeros. The frequency response now becomes this equation here. So now we apply the discrete time Fourier transform. So here the DTFT. And you can see instead of having our original signal x, we just keep every capital N's sample here, right? And then the sum only runs on the non-zero entries. So the question is, how does it change our spectrum here, the result of the DTFT, right? It should be different because we only keep every capital N's sample. Yeah, again, we can write downsampling as a multiplication of the signal with a sampling function. And this is helpful for this analysis. In continuous time, it was a sequence of Dirac impulses. Here it is a sequence of unit pulses at positions of multiples of capital N. So this is now a unit pulse train, So here it has the ones at all the positions that you want to keep and 0 in between. Then the sample signal with a 0 still in it simply becomes a multiplication of our original signal x times this unit pulse train delta n. Right? So this has all the unwanted samples zeroed out, but still has the same sampling rate because the zeros are still there. So this signal is now an intermediate signal which gets the zeros removed before transmission or storage to reduce the needed data rate. So the zeros don't really carry any information. The decoder upsamples it by reinserting the zeros to obtain the original sampling rate, which is easy enough if the decoder knows the original sampling rate. Observe that this is then also the signal that we obtain after this upsampling in the decoder. So it appears twice, in the encoder and the decoder. Hence this signal looks interesting to us because it appears in the encoder and also in the decoder. So what does its spectrum or frequency response look like? We saw the downsampled signal can be written as a multiplication of the original signal with the unit pulse train delta n. In the spectrum or frequency domain, this multiplication becomes a convolution, right? So this multiplication becomes a convolution with their Fourier transforms, right? A known result for Fourier transforms. Fourier transform turns a multiplication in one domain into a convolution in the other domain. Yeah, so the Fourier transform of the unit pulse train turns out to be a Dirac impulse train in the spectrum. But this is not so easy to derive, so we just apply a simple trick to show it, to make it mathematically more easy and get converging sums in the derivation. So we have a guess what the Fourier transform of the unit pulse train is. We get Dirac impulses at frequencies of 2 pi over capital N times some integer index k. Right? Yeah, maybe I should add that with integer index k equals 0, comma, dot, 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 comma, n minus 1. Right, basically it covers the frequency spectrum from 0 to almost 2 pi. Yeah, so this can be seen by looking at our sampling unit pulse train. Since it has a 1 every nth sample, that means we have a frequency of 2 pi over n. Right? So that's the normalized frequency of our unit pulse train. So basically this 2 pi over n is the fundamental frequency of our unit pulse train, and for the higher case we just get harmonics. So you can just imagine this unit pulse train as a periodic function, very non-sinusoidal, so it should have strong harmonics, and those harmonics, they appear at multiples of this fundamental frequency. That's why we have those integer indices. We also have a 0, which represents a DC component, right? And we get a DC component because this unit pulse train has all positive values, so the average of all of them will be positive. Yeah, so now we can apply it to our derivation. Remember that the inverse discrete time Fourier transform is this here, right? So now we have again an integral because our frequency domain is continuous. So the normalized frequency omega is continuous, but it is periodic, and that's why we only need to have this integral over one period from 0 to 2 pi. Right, so this is what we found, that we have this periodicity in the frequency domain. So we go over one entire period in the spectrum, and this is then the inverse discrete time Fourier transform. And here we can see we have the same transform kernel as before, just that there's a plus instead of a minus. and then we get this inverse transform, right? And here the integral runs over omega, the normalized frequency, instead of t for the forward transform, or n for the forward transform. Yeah, and here is our guess for our spectrum. So here we can see the harmonics that we expect in the frequency domain. We just assume each has the same strength, easy enough. We just say we have very strong harmonics, and then we have some factor in front of it, and it turns out later that this is a good factor, right? So for now it's not really so obvious, but it becomes obvious. So this is basically, this should be the Fourier transform of the unit pulse train. And we can test it by plugging this assumption into this inverse Fourier transform, and then we should obtain the unit pulse train here, right? So this is our test if our guess is correct. So now we can apply this inverse Fourier transform to our guess and use it in the time domain. So here we apply it, and right, so here we just plug this in here, right, and all we get is then the non-zero points of this delta, right? So what's left of this integral is the frequency points at frequencies 2 pi over n times k, and this k runs from 0 to n minus 1. So this integral here turns into this sum, right? Yeah, and then we have this factor here, which then comes in front of the sum, so the 2 pi cancels here, and what's left is this 1 over n. So basically this is then the result that we get after plugging this unit pulse train in the spectrum, in the spectral domain, here in this inverse Fourier transform. And this is what we get as the result. So this equality sign is still questionable, right? We still have to find out if this is really the case. So we have to prove that this is indeed true, since we only applied a guess. And to do that, we can take a look at the sum. It's a geometric sum, as you can see here. So this sum goes from k equals 0 to n minus 1. And then we have this sum index here appearing in the exponent of this exponential function. So you can assume this e to the j 2 pi over n times k is well, the other way around. This k is in the index here, and this n is assumed to be constant for each of those deltas. So given n, 2 pi over n is given anyway. Then you have this as a geometric sum, where this e to the j 2 pi over n times lowercase n is a fixed factor for each of those sums. So for each n, you get a different sum, right? And now we have to test what's the result of this sum for each lowercase n. And that's why it helps to see that this is a geometric sum. So here we have a sum of this shape, right? The c is this, right? You can see it here. The c is this e to the j 2 pi over n times lowercase n. And using this trick, we can simplify it, and we multiply the sum simply by the c. Then we get c to the k plus 1, right? And that's the same as having c to the power of k, but just shifting this index by 1, right? Same thing. And then we can take the difference of the two, and most of those summands will disappear except for the first one in this one and the last one in this one. So what we get is the last entry here, c to the nth power, minus the first entry here, which is 1. So then we can factor out the s. So we have s times c minus 1, and bring the c minus 1 on the other side in the denominator. And this is the result, right? S equals c to the nth power minus 1 divided by c minus 1. So this is now a convenient closed form where we can check out what happens for different n, right? And in order to get our unit impulse train, this sum must become capital N for n equals mn. Remember, this n is what we had as a factor before it, so this should become 1n, so that the entire thing becomes 1. And we can check this by simply plugging this into the sum here. The right part of the sum is undefined in this case, so if we have n equals integer multiples of capital N, then we have 1 minus 1, and this is also 1, and 0 divided by 0 is undefined. So this doesn't really work, but we get an easy result by looking at the left hand side. So here the n will cancel 2, so then we have the exponent here is 2 pi times some integer k, and that's integer multiples of 2 pi, and that means this expression will always be 1, and hence we have n summens of 1, and that means the sum is capital N. Right, so this is actually exactly as we need. For n unequals mn, so if it's not an integer multiple of capital N, we need this sum on the right hand side. So just plugging it in, we can see here this again becomes 1, right, independent of the value of n, because the n cancels. But here this n and this capital N doesn't cancel. So then we have 2 pi times some fraction, and that's unequal 0, and that means here the denominator becomes unequal 0, and then we have 0 divided by something else, and this is 0. Right, and this is also as needed. So now actually we get our unit pulse train using this sum. Right, so here we can see it. So we can replace our unit pulse train, which is mathematically a little bit tricky defined, and we replace it by this sum here, this finite sum of complex exponentials. And this looks more complicated, but is mathematically much easier to handle, and that's why we use it. So now we can plug it in to our discrete time Fourier transform. So here again is our discrete time Fourier transform of our sample signal x, and this is our unit pulse train now, where we replaced it by this sum. So here we can see the sum. I took this sum and drew it outside. So inside the sum now we have this infinitely long sum, and I can also combine those exponentials very conveniently. Right. So what we have now in the sum, in the exponent, is simply the sum of those exponents. So very convenient, because now we know what this looks like. So this is basically exactly the DTFT of x of n, but shifted in frequency by 2 pi over capital N times lowercase k. Right, so this is a frequency shift of omega, our normalized frequency. So then we can simply rewrite this inner term here simply as the discrete time Fourier transform of our signal x, but shifted in frequency. And since we still have this outer sum, we can see the frequency shifts sum up. So we also have the term k equals 0, so then we get the original frequency, and for the higher case we get correspondingly shifted frequency responses. So we see this consists of original spectrum plus shifted spectrum. That's an important result here. So we have multiple shifted versions of the signal spectrum, and these are the so-called alias components. We have n-1 alias components. So here I use aliasing as a term for those spectral copies, and sometimes in the literature you see aliasing, this term used only when you have overlapping spectral copies. And since we don't really know if it's overlapping or not, I call them in general aliasing. Yeah, so this is the result then. So in conclusion, sampling a signal by a factor of capital N with keeping the zeros between the sample points leads to n-1 alias components or spectral copies. Maybe I can add that, or spectral copies. So sometimes I also call them spectral copies. Or spectral copies. Right, so now we come to an example, a Python example. So we make a sine wave which at 44,100 Hertz sampling rate has a frequency of 400 Hertz at 1 second duration. Hence we need 44,100 samples and 400 periods of our sinusoid in this 1 second. Hence we can write our signal in Python. We start with IPython with PyLab. Right, and here you can see it. So here I'm starting in the terminal shell with this command, and then inside interactive Python we can enter those commands. So let me do that. So first I open a terminal window. So it's quite easy to open a terminal window in a given directory. I'm going to the Python examples here, but just right click in Ubuntu and say open in terminal. Maybe I should mention we do everything in Linux or Ubuntu, possibly also in Mac, but Windows doesn't really work. So you should have on all your laptops or computers, you should have Linux or Ubuntu Linux. I recommend a dual boot system. So you can download Ubuntu from Ubuntu's website, burn it on a USB drive, and then start your laptop from this USB drive by setting the start option of your computer to the USB drive, and then it starts from the USB drive in Ubuntu and lets you install this Ubuntu. Right, and in this way you can do all the work. And this works best because sooner or later with Windows you would get into trouble because some modules are not available or don't install. So that's much easier done with Linux and Ubuntu. And again, if you're not so familiar with Linux and Ubuntu, look at our other lectures like, for instance, ADSP or multirate. ADSP also has some introduction to Linux and the command line shell as I'm using it here. Right. So here you can see my command line shell. And I'm now starting IPython 3 --pylab. So here you can see it. And you can recognize it here with a colorful prompt. Oh yeah, and I should mention, if you didn't install PyLab, you can simply install it by sudo apt python dot python. I think IPython should work. So there's install missing. So this is also an advantage of Linux, that you can easily install missing software or missing libraries. So password needed. Oh, it's not available. Then maybe it works with Python dot. Interesting. Yeah, sometimes you have to look around a little bit before it works. Yes, this works. So IPython 3, it knows. And this is also important to know because Python used to have both versions, Python 2 and Python 3. And Python 2 became obsolete in the end of last year. So now everything is Python 3. If you have both versions, then you can distinguish them with a number in the end, which is the case for me. So I have both versions, so I need to have IPython 3. Yeah, so you can easily install it. You can also install PyLab accordingly. Sudo apt install python 3.pylab. Let's see if that works. Unable. Let me try this one here. Pylab 3. No. Then you can also try sudo pip install pylab. And it should be pip3 here. Interesting. It's not really working. So pip is the Python packet installer. And this contains many of the libraries that we will need. So Python itself and some of the main packages are available from the Linux Software Center and are installed using apt, as I did before. But some of the more specialized packages, they need to be installed with this pip command, this pip install. Right, and then you can install it in this way. Again, very useful. And for the pip, you also need to install it first. So that comes from your software center. Install pip3, probably python.pip. Python 3.pip. Somehow that's not really working. Yeah, so when you have this done, you can actually start your code in this way. So here you can see our Moodle 2 page, and then you just scroll down until you get to the lectures, and here you can see first lecture, and here are the Python examples. So for each lecture you can find the Python examples in this corresponding folder, and here you can see there's this sound function which you can then download, or you can simply download this folder as a zip file, for instance. Okay, so I would just type from sound import star. So this imports all the functions without names and without namespaces directly in my workspace here, which is kind of dangerous. So when you program, you shouldn't do it this way. You should do things like import numpy as np, right? And then you can specify each function within numpy as np.sign, for instance. And this is useful if you have two modules or libraries which have the same function but slightly different. For instance, the module scipy also has a sign function, but slightly different, and in this way you can differentiate between the two. Okay. So now you can play back the sound here, copy, and yeah, here I have a scaling because the sound card expects a 16-bit value range. So it's between -2 to the 15th to +2 to the 15th. And that's why I need to scale it, because the float values here, the sign is only between -1 and 1. So here, this is needed for the correct value range. And where am I? Here. Paste. So this was our 400 Hertz tone. You can also plot it. So indeed we see those sine waves. Here are the first 100 samples, nice sinusoid, right? And now we can multiply the sine tone signal with the unit pulse train with capital N equals 8. So we want to do downsampling by a factor of 8. And for that we use this indexing trick to get the desired result. We initialize an array with zeros for 1 second. And then we assign only every 8th sample by including this step size 8 here. So we start from 0 going up to 4100 and only address every 8th entry, every 8th index. So we have index 0, 8 and so on. So here we assign only every 8th index from the original, and the rest will stay 0. So let me do this. Copy, paste. Right, so this is the initialization, and here we have the assignment of every 8th sample. Right, and now we can plot the first 100 samples, see how it looks like, and this is what we get. Right. So this is exactly what we expect. So here we have the sinusoid, but we only keep every 8th sample, and in between it's zeros. And we see those little lines, they are not really there. That's basically an artifact from the plot function. The plot connects points, right? So the plot function connects this sample with a line. We could also use, for instance, stars. Then we can see individual samples, and here we can see that those lines are not really there, right? We have sample here and zeros around it. So these are the 7 zeros after each sample. Yeah, so this is what we just saw. And now we can take a look at the resulting spectrum, right? And now the just mentioned SciPy. So we import the library or the module SciPy signal. So this has a submodule or sublibrary signal, and give it a short name SPS for convenience. So going back, that's not what I want. So here I import it, and now we can use Fraxi. Fraxi basically computes the discrete time Fourier transform for a given number of spectral sampling points, right? So that's convenient. So here I compute this, copy, paste, and then I plot the magnitude. So here the W contains the frequency sampling points as normalized frequencies. Right, so they actually go from 0 to pi because we have real valued signals, and for real valued signals we have this symmetry between positive and negative, or between 0 to pi and pi to 2 pi. So this is the frequency axis, and H contains the complex values of our DTFT. Here we only plot the magnitudes, because it's easier to visualize, right? So we now plot it. And this is what we get. So also more or less like we expect. Horizontally we have the frequency from 0 to pi, 3.14. And then there's a strong peak at the frequency of the sinusoid, right? This is the normalized frequency here. So we can actually zoom in, and we can see it's around 0.05, right? So going back. And basically not much else. So here we have almost nothing. Here we have some ripples, but this is just an artifact of having a finite length DTFT applied to our signal. So these ripples are an artifact from applying the DTFT here in Fraxi. Yeah, so this is what we get. Yeah, and we can check the normalized frequency. So normalized frequency. Here we have the Nyquist frequency as 22,050 Hertz, so pi corresponds to 22,050 Hertz, and hence our sinusoid should appear as a peak at normalized frequency of 400 Hertz divided by 20,050 times pi, which is 0.057, which is indeed what we just saw. So now we can compare this to our downsampled signal. All right. Oh, I actually closed it. I should have left it open. So here it's open. So now we can do the same with downsampled, including the zeros. So downsampled, upsampled. Let's just copy everything. Copy, paste. And let's take a look. And this is what we now have. Right. So this is kind of interesting. Now we can directly compare. So this was the original, and the orange one is now the downsampled one. And you can see here we have those shifted versions. And then you have those pairs, and they basically come because of the symmetry between positive and negative frequencies. Remember, when we have negative frequencies, this axis would continue here. You would have the conjugate complex, which means the magnitude would be just mirrored around 0. So there's another peak coming at this negative frequency of 0.05. And this is what you can see here. So the entire thing is shifted by 2 pi over 8. And you can see here the spectral copies. And you can also see that the original sinusoid is much weaker because now the energy is distributed also over the spectral copies, and also we only keep every 8th sample, which means we lose most of the energy of our signal, and that's why this is so much lower. Yeah, so this is what we got. So we have altogether 7 new aliasing components or spectral copies because we did the downsampling by 8, and this is what I just explained. They also close together because of the negative frequencies, where you also have a peak at minus 400 Hz or minus 0.057. Yeah, often the small magnitude components in this plot are also interesting, and for that reason magnitude frequency responses are usually plotted on a logarithmic decibel scale, applying the function 20 times log 10 of it to it, which can be seen here. So I'm making a new figure, copy and paste. And now you can see the same, but on the logarithmic scale. So you can see the peaks, and now you can also see all those little ripples here, which before we didn't really see. And as I mentioned, they are actually artifacts from applying a limited finite length DTFT or DFT to the signal. Yeah, so this is the result. Now we can also listen to the signal, including the zeros. So this should not sound good. Copy, paste. So you could hear the original at much lower loudness, and you can also hear those higher pitched tones, which are the spectral copies again. Yeah, so these are now the harmonics from doing the sampling. So, or the spectral copies from doing the sampling. So basically we just heard this spectrum here. So this is still the original, and here are the spectral copies, which are now becoming obvious when you listen to it. Yeah, so in general you don't want to hear those alias components or those spectral copies, and hence we need to find out how to get rid of them. Yeah, here's a real-time Python example. First we take a look at the signal from the microphone to see its amplitude fluctuations. To run the script you need Python installed, and additionally its library Python PyAudio. Yeah, so also Python matplotlib and Python matplotlib animation. So this animation is often not installed by default, so you would need to install it with sudo apt install. And then you can just use the script which I provided in Moodle. So I just exit here. And we can take a look at it. Here, first I open this with an editor. Copy. So here I'm using gedit. So gedit is a very nice editor which is included with Ubuntu Linux, and I found it quite useful. And paste the name. So here I'm already in Python example, so I already have all those Python programs available. You need to download it from the web page. And here you can see what's inside. So here you can see import PyAudio. So this is the module or library which allows you to access the sound card, which is important for this example. Yeah, here's an animate function which basically reads a block of samples from the sound card and turns it into an array of floats, right? So here's a conversion from 16-bit integer and then to float. And here it plots it. And here you initialize the plot. Here you open the sound card. Here you test the sound card. Here you assign, here you actually open the sound card and assign a pointer to it. Here you set the number of channels. In our case it's mono. So this should be 1. The rate, let's see, what did I set here? The rate here is now 32,000 samples per second. We have 1 channel, mono. We have a chunk or block size of 1024 samples. So it reads 1024 samples with each access to the sound card. And this is the total length that it plays back. Yeah, so here it initializes the sound card with the desired values. And here it actually does the animation. So here it calls the function animation to do the live plot of our microphone signal. So I can now let it run using Python 3. This is a test. 1, 2, This is a test. B, C, D. Yeah, so you can see it's working. And this is basically how the output of your sound card looks like, right? This is how the audio signal that comes from the microphone looks like. You could see those waves when you whistle. You have more sinusoidal-like tone, so you have those more or less regular waves. If you speak, it's a mix of waves and noise-like waves. Yeah. We can also do the sampling, and for that I have this program here, sampling block. This does the sampling. So let me first open it in the terminal shell. So observe here I'm in the terminal shell, not in IPython. So it starts basically the same. Here the block size is larger because I also play back to avoid a feedback. Here width is 2 bytes per sample, 16 bits. That's the usual. Mono, 32 samples per second as before, 8 seconds. Setup is the same. Here I'm not really doing an animation. That's why I have a simple for loop here, reading in the samples as before. Here I have an array or a list of shorts in samples. Then here I have my sampling unit pulse train. So I'm using downsampling by a factor of 4. And yeah, this uses a slightly different approach. Here I have an array of a range type. So this counts up, right? And basically I'm looking at I'm applying the modulus function here. So it looks basically makes an integer division by n, and it looks if we have a remainder or not. So this has a 1 at every 4th sample in this case, and 0 in between. And then I apply the unit pulse train here to samples and then write it back. Here converting it first to 16-bit integers, and here I write it back to the sound card, and then we can listen to it. So now we apply the sampling by a factor of 4 to my voice. So I started with Python 3, and in the argument we have the program name. Test, this is test 1, 2, 3. So you can hear the spectral copies of those chirpy sounds. So it sounded really chirpy, right? And that's basically those spectral copies which appear at higher frequencies. So that's not good. They're really obvious. So here you can hear the microphone signal as it is sampled at 32 kHz sampling rate and then multiplied with a unit pulse train and then played out again at 32 kHz sampling rate. So you can hear the high frequency aliasing artifacts which sound a little bit like ringing, right? You can play with the script and see how the sound changes when you change the downsampling rate, capital N, in the script. So since this is available to everybody of you, you should download it and see if you can get it to run on your computer. So this is instructive because you can listen to your own voice and listen to what happens when you do the downsampling with spectral copies. And also you can test if your software is running, right? Install PyAudio and install what else might be needed on your computer and see if you can get access to your sound card, because this is all necessary for the seminars. So everybody should be doing this test using this function to see if it works. Also to see if your software works in this context, right? If you have access to your sound card, if all the desired libraries are there, and if Python is running. So it's twofold. See the effect of sampling and then test your software system or software setup. Yeah, so next would be removing the zeros when you do the compression. The final step of downsampling is now to omit the zeros between the samples to obtain the lower sampling rate. And let's call the signal without the zeros y of m, where the time index m denotes the lower sampling rate, as opposed to lowercase n, which denotes the higher sampling rate. So in our Python example, it would be like this, right? Again, you use the indexing trick. So I give it a slightly different font. And here's what you get, right? So basically, when you drop the zeros, it looks very smooth again because the plot function connects the samples with each other. So let me do that. Oh, I closed my IPython window. So let me go to my IPython window. And actually this memorizes what I did. So I just need to have an up arrow to do the previous stuff, right? So here is, here's my signal S. Oh, yeah, first I need to X. So X equal, it also has auto completion, so I just enter X and then type the up arrow and then we get the X back. Then S equal up arrow, we get the sign back, very convenient. Then SD equals up arrow, not working. SDU equals, so here we have the initialization with zeros. SDU equals yeah, and there we need the unit pulse train. Yeah. Okay. Yeah, so this is our SDU. And then we just saw plot SDU. This is basically the one where we have all the zeros inside. That's why you don't see much here. When you zoom in, then you can see you have sample, and in between you have zeros. Right, now we just keep the non-zero values. We just throw out the zeros, copy, what's happening here? Invalid syntax. Sometimes that happens when you do copy and paste. Don't know why. No, SDU. Let me type it, that's safer. SD equals, oh yeah, I think the equal sign was a problem. SDU of 0 colon 0 colon 44,101 to get the last sample in steps of 8. No, that's strange. Oh, of course, it should be square brackets. So if you come from Octave or MATLAB, it's round brackets, but Python is using square brackets. So that's something to keep in mind. So this is our SD. Yeah, that works. So there's also a problem here. Oh, Jesus. Okay. And the same here. So the argument of arrays always uses square brackets. So here the round brackets are for functions like plot of. So these are round brackets, but the index of arrays always uses square brackets. And this is just an expression here, 100 divided by 8. So this reflects the new sampling rate. So now we want to cover what before we covered with 100 samples. Now we cover with 100 divided by 8 samples. So let's try that. Plot SD of 0 up to 100 divided by 8 square brackets, round brackets. And here we need to have 2 slashes. That's also interesting because that's a change from Python 2 to Python 3, because in Python 3 division always results in float values, whereas in Python it was an integer. And here you get the same behavior by using a double slash. So here double slash means you just have the integer of division. And that's important because this is supposed to be an index, and an index is always integer valued. So here we can see we have now part of the sinusoid, but with only 10 or 11 samples. Right, so this is what we can see here. Yeah, or here 12 samples. Yeah, so how are the frequency responses of y of m, the downsampled version, and xd, the one still containing the zeros, are connected? We can simply take the Fourier transforms of them. So here is the Fourier transform of xd. So just the usual Fourier transform. And here I have the Fourier transform just over the non-zero entries of xd, which is basically y of m. So here we can now include y of m here. So that's our xd of omega when we have this index substitution here. And then you can see, because of this index substitution, we get this factor capital N in here, right? And when you look at this expression here, this is just the Fourier transform of y, the downsampled version, but with a scaled frequency axis omega. So now we have, instead of omega, we have omega times capital N, right? So that's the result. Basically, when we downsample, we multiply the frequency axis accordingly. That means we go over the frequency range more quickly. So we reach 2 pi much more quickly. So what was before was pi over n, now becomes pi, right? And it shows that the downsampled version with the removal of the zeros has the same frequency response, but frequency variable omega is scaled by the factor of n. For instance, the normalized frequency pi of n before downsampling becomes pi after removing the zeros. It shows that a small part of the spectrum before downsampling, up to pi over n, becomes the full usable spectrum after downsampling, because it becomes pi. Observe that we don't lose any frequencies this way, because by looking at equation 1, we see that we obtain multiple copies of the spectrum in steps of 2 pi over n after the sampling, and hence the spectrum already has this periodicity of 2 pi over n. This means that the spectrum between minus pi over n and plus pi over n, for instance, we could also take any period of length 2 pi over n, contains the unique and full part of the spectrum, because the rest is just a periodic continuation. This can be seen also in these following pictures. So here we have some fantasy spectrum, here the negative frequencies, here the positive frequencies, and those boxes could be, say, an ideal band pass or an ideal high pass here. So this is the upper half of our frequencies, which it keeps and then zeroes out the rest. So after filtering, this is what we keep. Then we do the downsampling by a factor of 2 in this example, and we get those spectral copies. So this is copied here, and this is copied here. Right, so this goes here, and this goes here. But they are touching, but they are not overlapping, as you can see here, because we use ideal filters. So that means we can also still separate them, because they are not overlapping. So here we have the signal spectrum after multiplication with the unit pulse train for capital N equals 2, hence setting every second value to 0. The zeros are still in the sequence. Observe that we shift and add the signal by multiples of 2 pi over 2, in this case pi, right? So that's why this goes here. And we obtain mirrored images of the high frequencies to the low frequencies. So it looks like this is mirrored here. In reality, this comes from the negative frequencies. Observe that the mirrored spectrum and the original spectrum don't overlap, which makes reconstruction easy. So this is then what we obtain after removing the zeros. So now we scale it. So what was pi over 2 before now becomes pi. Right, so we have the stretching. And in conclusion, removing the n-1 zeros between samples stretches the spectrum of the signal by a factor of capital N. Yeah, and then in the decoder we do the upsampling. What is still missing in our sampling, in our system, is the upsampling as the opposite operation of downsampling, for the case where we would like to increase our sampling rate. One of the first approaches to upsampling that often comes to mind if we want to do upsampling by a factor of capital N is to simply repeat every sample n-1 times. But that's bad. But this is equivalent to first inserting n-1 zeros after each sample and then filter the resulting sequence by a low-pass filter with an impulse response of capital N ones. And it turns out this is a special case which is not good. So that does not give us a good low-pass filter. So this is a very special case, and we would like to have a more general case. Hence we assume that we upsample by always first inserting n-1 zeros after each sample and then have some interpolation filter for it. For instance, a good low pass. Again, we can take the signal at the lower sampling rate, or in the last case it would be a good high pass, right? So let's take a look. We take the signal y of m at the lower sampling rate. M denotes the lower sampling rate. Now we want to do the upsampling. First inserting the zeros, we get xd back, right? And lowercase n denotes the higher sampling rate. Yeah. So now we can take the result from downsampling. We get the same relationship. And in effect, by upsampling, we shrink the frequency components. We are now just coming from ym going to the now upsample signal. For instance, we had the frequency pi before upsampling. It now becomes pi over 2 for the upsample signal if we have n equals 2. In this way, we now get an extended frequency range. Since the spectrum before upsampling was also 2 pi periodic, the extra spectrum we obtain contains a periodic continuation of our spectrum, which again is aliasing, which we would like to suppress using filters, low pass or band pass filters after upsampling. Yeah, so we saw the effects of downsampling and upsampling, and observe that we can perfectly reconstruct the high-pass signal in our example if we use ideal high-pass filters in that case. In this way, we have the following analysis and synthesis, like in this following picture. So here on the left, we have our encoder. In this case, we have a high-pass part, right, which just keeps the high frequencies. Even though they are high frequencies, we can downsample it by this factor of 2. We keep this middle frequency range, which consists of the mirrored spectral components. Then in the decoder, we would do the upsampling by a factor of 2 by inserting the zeros. We would get this extended frequency range where we get those spectral copies now, the repetitions. And then we apply the high-pass filter again to fish out the original spectral components here. So you can see this not only works for low-pass signals, but it also works for high-pass signals. Yeah, so observe that in this case we violate actually the conventional Nyquist criterion because our high-pass passes the high frequencies. But then the sampling mirrors those frequencies to the lower range such that we can apply the traditional Nyquist sampling theorem there. This method is also known as bandpass Nyquist. This is an important principle for filter banks and wavelets because there we have many filters, not just low-pass filter but also bandpass and high-pass. So it says that we can effectively reconstruct a bandpass signal in a filter bank if we sample with twice the rate as the bandwidth of our bandpass signal, assuming ideal filters. So in this example that we just saw. Yeah, and these effects that we just saw in the DTFT domain work the same in the Z domain. So you should all be familiar with the Z transform. So here's the one-sided Z transform, which we always use because we assume that we have causal signals which start at some point in time. So this time point is then n equals 0. But it might continue to infinity. Right? Basically it says, this infinity says that it starts at some point, it stops at some point. So in effect, the Z transform turns our sequence of samples into a polynomial. Right? When you look at it, this is just a polynomial. Right? We have factors and exponents of Z. And this Z is our argument of the Z transform. Right? Before we had our argument n, the sample index. And after this transform, we have a big polynomial where Z is our argument. And Z is basically a more abstract frequency domain variable. So observe that the multiplication of the Z transform with Z to the minus 1 can be interpreted as a delay by the signal by one sample. Right? So if we have a delayed signal which starts, say, at n equals 1, then you would have the first entry Z to the minus 1 here, and that's the same as if you would start here with n equals 0 and multiply with Z to the minus 1. Right? So a delay by n samples is simply becoming a multiplication of Z to the minus this delay. And that's one of the big advantages of the Z transform, that a delay can be written as a multiplication. Right? And that means when we have in an expression, in a sum, we have different delays, then we can simply factor out the delays. Or we can factor out the signal, the undelayed signal, and have a sum of delays. Yeah, first observe that we get our usual frequency response if we evaluate the Z transform along the unit circle in the Z domain. So if we replace Z by e to the j omega, plug it in here, we see that it's exactly the DTFT. Right? So the DTFT is a special case. What is now the effect of multiplying our signal with a unit pulse train in the Z domain? And to see that, we simply apply the Z transform. So as we did before, now we just do it in the Z domain. Here our sample signal, applying the Z transform to it. And you can see the result is almost the same, except that the argument now, instead of having a shift of omega, we have a multiplication of e to the minus j 2 pi over n times k, this frequency copy, this frequency index. And when you look at it, z is basically e to the z is e to the j omega, right? As we saw here, we just plug it in to get the connection, and then we can see we have this plus omega, the normalized omega, and that's basically the same as in the Fourier transform domain. Yeah, so it's basically the same, very similar, just that we now don't have frequency shifts for the aliasing term, but a multiplication of the exponential functions to z, as we can see here. Next, the removal or reinsertion of the zeros, which you can see here. So again, we do the index substitution and we get this exponent here, right? So instead of having omega divided by capital N, we have z to the power of 1 over n. And again, you can see it when you replace z by e to the j omega, then again you have omega divided by capital N. So it's the same thing. Yeah, another very useful tool is the so-called modulation. This is the multiplication of our signal with a periodic function, for instance an exponential function, and it can be written as this expression. So here you have your samples and you multiply each sample with this periodic exponential function. So this has a periodicity of 2 pi over omega n, and its Z transform hence becomes this. So basically this exponential function here becomes part of the Z, multiplicator of the Z, and it basically rotates the Z accordingly, and that means when you replace Z by e to the j omega, you just add this omega m to it. So it's the effect of simply shifting the frequency response by omega n m. So that's also an interesting result. You can shift up and shift down in this way. Yeah, and this actually can be seen here in this little example. I actually again did it with live audio. So first I need to quit my IPython to go back to the terminal. And let's first take a look at this program. So here it starts the same as before. Here we do the for loop. And now instead of having a unit pulse function, now I have S as a sinusoidal function with a corresponding frequency. Right? Well, not really corresponding, but at some frequency. So here I have some frequency offset, which is defined somewhere. That's 128 times 4. Yeah, so basically it's the frequency is pi divided by 4 times 128. So some low frequency. And then we multiply it here with the samples and then write it back to the sound device. And again, here rather high block size because I want to get some delay to avoid feedback. So now when I try it, you should hear a frequency shift in my voice. So let's try Python 3. Okay, so this is again a case of not really compatible with Python 3. So let me open it, gedit. Oh no, it's already open. I don't need to open it. 53. Yeah, so here samples equal samples dot s int, I think. First we need to turn it into an integer. So let me try it again, Python 3 as type int. Type int. Let's see. Okay, I forgot an S here, so now it should work. Let's try. So this is actually how you convert an array of floats to an array of integers. So here, because of this S, samples was an array of floats. And if you cast it as type int, then it turns it into an array of integers, which is what this MPEG, struct PEG function expects. So here, this should be an array of integers. So let's try. Test. Test. So very short. Test. So there was actually an overflow. But you could hear my voice was much higher, like a Mickey Mouse voice, right? And this is the effect. I was shifting my voice to higher frequencies, and it turned my voice into a Mickey Mouse voice. Yeah, an interesting case is also obtained if we set omega m, this modulation frequency, to pi, right? Very high, the Nyquist frequency. And then the modulating function is just a sequence of plus minus ones, and multiplying this with our signal results in a frequency shift of pi, right? If we have real valued low pass signal, for instance, this will then be shifted by pi, and we will obtain a high pass. So this looks funny. Yeah, and in this way we can turn the impulse response of a low pass into a high pass and vice versa. So here is the frequency response of our low pass, and then we shift it by pi, so we shift 0 to pi, and then we get a high pass accordingly. So the other half would be appearing above pi. An important tool is the reversal of the ordering of a finite length signal sequence with length L, meaning x of n is non-zero only for the region between 0 and L minus 1, and we just flip it, right? And then its z-transform is simply this. And then we can do the index substitution, replacing n by the reversed n prime. So n is replaced by n minus 1 minus n prime. So now n prime basically goes backwards. And that means we flip this and then we flip it again. And then we have this n prime. So this goes forward again, but now we have the flipping here in the exponent. Right, and this n minus 1 is a constant which we can factor out, put it in front of the sum. And what's left here is this negative index now. And this negative index, this minus 1, has a consequence of the argument being now z to the minus 1. Right, so we can say the z transform of the reversed sequence is the z to the minus n minus 1 constant times the z transform with this flipped exponent in the argument. Yeah, so this inverse of z in the z transform signifies the time reversal, and the factor of z to the minus l minus 1 is simply a delay of l minus 1. So first we flip it, then we have negative indices, and then we delay it such that all indices are positive again. Yeah, and finally, quickly, mid-rise and mid-tread quantization. That's the two main quantizers. Depending on if the quantizer has the input voltage 0 at the center of a quantization interval or on the boundary of that interval, we call the quantizer a mid-tread or mid-rise quantizer, as illustrated in this. So here is a mid-rise. So 0, this is the input axis. And if it's a little bit positive, it jumps up. If it's a little bit negative, it jumps down. Here's the mid-tread. Here the input needs to exceed the value of delta over 2 plus or minus to get an output with a corresponding sign. Right, so here small values are swallowed. Small values are rounded to zeros. Here small values become actually quite large because they always jump up or down. Yeah, and here you can see the corresponding equation. So for the mid-rise you have a floor operation for the quantizer, and then adding half the quantization step size for the reconstruction. And for the mid-tread you have a simple rounding operation. You take a function value divided by the step size, the quantization step size q, and then round it, and then you get an index, the quantization index. On the decoder you just multiply this index with a quantization step size to get the quantized value back. Yeah, so here this q is the index after quantization. So this index is then an integer value. Yeah, and Q of f is the reverse quantization, which produces the quantized reconstructed value, which basically has values which are jumps in the size of q. So q is the quantization step size, which is identical to delta in the plots. Here you have the delta, right? So that's identical to this q. Yeah, and then we can also define a quantization error by taking the reconstructed signal and subtract the original signal or value, reconstructed value, original value, and that's your error, the quantization error. And it turns out that the quantization error in both cases, if you have uniform quantization noise, meaning if the signal is much larger than the quantization step size, then you can compute the quantization error power as delta square over 12. So you just need to know the quantization step size, and then you can compute the average quantization power, quantization error power. Yeah, and here's a little example to show how they behave. So let me open it. Copy. So gedit. Yeah, so beginning is the same, and here I'm doing the quantization. So here mid-tread, so simply rounding for the quantization, and here the dequantization, simply taking the indices and multiply it by the quantization step size Q. So here you have Q, and here I actually have a larger, relative large Q. Right? When you think about maximum value here, 32,000, then this is 16 steps are sufficient to cover it. So this is leads to significant quantization artifacts. So on one side you want to have few steps because that reduces the bit rate that you need to encode it. So if the indices are just small, you just need a few bits to represent those indices, which is good for compression, right? But on the other hand, you don't want to make Q too big because then it becomes noisy, as you will hear. So here's the example, again using Python 3. Same problem. So samples equals samples dot s type int test. Yeah, unfortunately there's a lot of feedback. So at least here you could hear that it took a while. In the beginning was quiet, and that's because the small values were all rounded to 0. Right? That's the characteristic of a mid-thread. So now I can go to a mid-rise. So here I'm doing the flow operation. Here's the dequantizer. Here is the quantizer. So here's the flow operation. Here multiply plus Q over 2 because of this flow operation. And try it again. So here you could hear that in the beginning there was noise already there, right? And this is because small values, small noise is amplified in this way, right? So that's why usually a mid-thread is used. It leads to less noise and it's easier to encode. Right. Yeah, so both quantizers distort the signal audibly, so we need more bits for smaller quantization step sizes. So that's actually the art of audio coding, to choose the right step sizes for the right frequencies. Yeah, so this is what I just said. Yeah, and this should be it for today. So this was a little longer session because it covers the basics. Yeah, so now you should have a refreshed memory of all those basics. So thanks for your attention and see you next time.